RF. T naught is equal to the TC. At R is equal to the RC. TC is equal to the T naught. Now from this we can get C2F. So the next equation will be the temperature profile. Next equation will be the temperature profile. Temperature profile TC. Evaluate temperature at R is equal to the RF. So the TC at R is equal to the RF. So from this we can get the TC is equal to the So we will rub this first of all. At the here we don't have convective, we only have the heat conduction. So these terms are getting cancelled. Plus rate of energy in by molecular transport minus rate of energy out by molecular transport. Now here the molecular transport is nothing but the heat conduction plus rate of work done on system by molecular transport. Minus rate of work done by system by molecular transport plus rate of work done. Rate of work done by the external forces. By the external forces plus rate energy production plus rate energy production. which is equal to 0. So from this we have doesn't need the convective transport because the in question they have mentioned the conduction, heat conduction. So we'll cancel out this, and the molecular work done by the molecular transport is also not there in question. So we will neglect these terms. So we only got rate of energy by molecular transport minus rate of energy by energy out by molecular transport plus rate of energy production. Rate of energy in by molecular transport minus rate of energy out by molecular transport plus rate of energy production is equal to the 0. Now we have seen the limit, which is we have applied the boundary conditions Sn r square, then we have seen the d by dr r square qrf. Now the heat generation, given heat generation Sn is equal to the Sn naught 1 plus B by R divided by Rf whole square. Combining this equation, d by dr is equal r square qrf is equal to the Sn naught 1 plus B R by Rf whole square r square. Now this is the boundary condition, differential equation for nuclear reactor. Now the differential equation for the aluminum cladding, differential equation for the aluminum cladding is the d by dr r square qrc is equal to 0. So here the no heat generation, so due to this the Sn is equal to the 0. Here there is no heat generation, due to this Sn is equal to 0. Now from this equation we can get the d by dr r square qrf is equal to the Sn naught 1 plus B R by Rf whole square r square. Now rearranging this equation, we will get the d by dr. Rearranging this equation, rearranging this equation, d by dr, r square q r f Sn naught r square plus b r to the power 4 r f to the whole square. This we will get. Now further rearranging this equation, we will get q r f is equal to the Sn naught r by 3 into b r f square r cube divided. Now we will write the notations of QRF, QCF. So the heat flux is fissionable material is equal to the QRF. Heat flux at radius r is fissionable material at QRF at R. Surface area of the sphere, surface area of the sphere of radius r is equal to the 4 pi r square. Rate of heat in conduction at radius r is equal to the QRF at r 4 pi r square, which is equal to the 4 pi r square QRF at r. Now we have got the four equation. Heat flux is fashionable material at QRF. Heat flux at radius r is fashionable material at QRF at r. At r is equal to r. Surface area of the sphere at radius r is the 4 pi r square. Rate of heat in conduction at radius r is 4 pi r square into QRF, which is flux into area. Now we will discuss the outer radius of the rate and surface area heat flux. Now the outer radius of the heat flux at radius r plus delta r fissionable material is equal to the QRF at r plus delta r. Now the surface area of the sphere of radius r is equal to the radius r plus delta r is equal to the 4 pi r plus delta r ka whole square. Now the rate of heat in conduction at r plus delta r, rate of heat in conduction at radius r plus delta r is equal to the 4 pi r plus delta r ka whole square QRF, which is r plus delta r is the negligible, so we consider the only r, which is 4 pi r square QRF, which is equal to the Sn. Now we will discuss this, we will put in the shell energy balances. Shell now the d by dr r square QRF is equal to the Sn naught 1 plus b r by rf whole square r square. Now the d by dr r square QRF, which is equal to the 0. R square QRF Sn is equal to the Sn naught r to the power 3. After the integrating this equation, we get the Sn naught r cube by 3 plus b r to the power 5 divided by 5 r to the power 5 plus C1f. From the first equation, we will integrate this one. So after integrating this, we will get the C r square QRF is equal to the C1f, which is QRF is equal to the C1f divided by r square. So how do we figure out how the heat actually travels outside? A shell energy balance. So imagine this spherical shell, it has inner radius of the r, okay, and outer radius of r plus delta r. It's a small change in radius, okay. Yeah, so shell energy balance basically says the amount of heat flowing inside the shell plus the heat generated within the shell must be equal and the heat flowing outside of the shell. So that's the heat. So it's not like a heat coming from the outside and heat is being generated. So everywhere inside the material, everywhere, okay. So that's our volume source. That's right. And we have talking about the region from the very center of the sphere where r is the 0. Outer edge of the fuel, which is the RF. So what's actually happening in the fundamental level, we are going to talking about the generated internally, but actually going on. So you have the nuclear reactions happening, right? Fission reactions where the atoms are splitting, and when they are split, they release lot of energy, and energy is carried by various particles, fission fragments and neutrons. As these particles move through the fuel, they collide with other atoms, and the collision transfer energy to the atoms, essentially making them vibrate faster, right? And that's what the heat is, vibration of the atoms. We are just smashing things around and creating all the motions. So we are going to talk about really intense burning at the center, and as you move the outward and kind of little cooler little bit. So our mission today is to understand how the temperature changes inside both the fuel and the aluminum cladding, and we are going to take that the using principle of the heat conductions. The key is that you have so kindly provided. So we are not just going to describe the science here. Now the temperature is constant with the theta and phi. Temperature is varying with the radius, that is T of R. Now the Newton's law of cooling, which is Q is equal to the H naught T naught minus TA, which is equal to the Newton's law of cooling. Newton's law of cooling. We will see the sphere. The outer sphere is the aluminum cladding, and the inner sphere is the sphere of reasonable material. Outer sphere is the aluminum cladding, Inner sphere is sphere of reasonable